right, so what are we doing today?
Defining
Defining ln. All right, so let's do that. Ha, there it is. Okay, we're done. Go home.
Are we gonna find the derivative too, or?
Yeah, imagine that.
Whoa.
Wow.
Crazy.
Crazy talk. All right, kindly consider the following function, cap f, which is the integral from 1 to x of 1 over t dt. Okay. First of all, what's the derivative of cap f? What's cap f prime? 1 over x, right? Okay, so didn't we say somewhere along the line the derivative of ln of x is 1 over x?
Yeah.
So this is how I'm going to define. I don't have any. Yeah. Alrighty. So let's show that that's ln. How about we make a little table of values? Okay. Let's say for different values of x, let's calculate f of x. For 1, well, 1 is easy. Do it in your head. Go ahead. 0, right? The area from 1 to 1 under this curve has got to be 0. From 1 to 1, right? Nothing. Okay. All right. Then from 1 to 2, from 1 to 3, and 4, and 6, and 8. And what I'm going to try and do is show you that this is logarithmic. You know the properties of logs, right?
Yeah.
The log of a product. Let's do it this way. The log of 2 times 3 is the log of 2 plus the log of 3, right? The log of 8 divided by 2, the log of 8 minus the log of 2. The log of 2 to the 3 is 3 times log of 2. And because I just said 1. I just used all the numbers I just said. I didn't even use 3. Did I use 3? I did use 3.
You didn't use 5.
I didn't use 5, right. I just said I'm gonna do what's the log of 2 times 3, so I need that. And I need 6. What's the log of 8 divided by 4, so I need that. 8 divided by 4 is 2, 2 times 3 is 6.
But why are those
So 8 divided by 2 is 4, and 2 times 3 is 6. I need all of those, see?
why?
Because I want to show you that the log of 2 times 3 is the log of 2 plus the log of 3. I got to figure that out.
You're
Right?
just showing
I want to show you that log of 8 divided by 2 is the log of 4. I want to show you the log of 2 to the 3 is 3 times log of base 2. So I need all of these, but 1 is in there for free. All right, so let's calculate this thing. Bing. All right, let's make a calculator page. Let's do the integral. All right. Did I actually make this a function? Let's see, let's try that. What if I do menu, calculus, 4, not 4, stop it. Stop it. Menu, calculus, and 3. Okay. I'm gonna type exactly what we had. 1, the limit, the integral from 1 to. It already died. Ain't you good at this? All right, from 1 to x of the function. Let's do a rational 1 over t with respect to t. Let's store that. Control var is store, right? Oh, not there. Not there. Control var is store. Let's call that f of x. And I'll just call it lowercase f of x. All right, f of x. All right, there you go. So is f of x recognized? What happened? F of x, yeah. You see, what am I looking for? That's good. What? Bold. Italics, not italics, bold, non-italics. That means it recognizes it. So I need f of 1, which we already figured out was 0, right? Right? Okay, so let's figure out f of 2. Let's see. F of 2. And look what it did. Oh, bad calculator. I didn't want that. Okay, let's do a numerical answer. 0.693, okay, so roughly. Okay, what about f of, I'm going to write down these in the table in just a minute. F of 3, control enter, I want a decimal here. 1.099-ish, right? F of 4, I got that all right here, so I'll just copy it down in a second. let's see, f. It's interesting that it's bold here, but then when you plug in a number, it's not. That's weird. Right? When you hit enter, it goes away. And yeah, I know. I know. Yeah. 1.386 and so forth. All right, so the point is that I know these values. Okay, what are they? All right, so it's 0.693, ln of 2. ln of 3, 1.099. ln of 4, 1.386, and we could have kept on going, but I got tired. 1.792 for the ln of 6, and 2.079 for the ln of 8. So is this a true statement? Isn't it? Well, it's within round-off error, but f of 6 is 1.792, and that's 2 times 3, so that should be f of 2 plus f of 3 if it's logarithmic, and f of 2 is this, and f of 3 is this, and you add them up, you get that, don't you? You do? Ooh, nice. Nice. Okay. All right, how about this one? Is the f of 2 the same thing, is f of 2 the same thing as f of 8 minus f of 2? No, 4? 4. Right? Because 8 over 4. So the log of 8 over 4 is the log of 8 minus the log of 4, but the log of 8 over 4 is the log of 2, right? So is the log of 2 the same thing as the log of 8 minus the log of 4? Well, this minus this. Very close. Yeah, pretty close. How about this? Is f of 8 3 ln of 2? No, not ln, stop it. F of 2. So if you triple f of 2, do you get f of 8? Pretty much, yeah, you do. Okay, good. Alrighty. So it is logarithmic. It has all the log properties that you know. The log of a product is the sum of the logs. The log of a quotient is different from the logs. The log of a power is the exponent times the log of the base. That kind of stuff, right? And the derivative is 1 over x. Like we said long ago that the derivative of ln x was 1 over x. So this is ln. That's what this is. Just to make the point. Okay, there you go. So that's ln, and that's why the derivative of ln is 1 over x. Okay, so what do you do with this stuff? Well, now, wait a minute. I didn't prove that it was ln. I proved that it was logarithmic. How do I prove that it's ln? Well, what do you mean? What didn't I show? There are a lot of different kinds of logs, right? What? How are they different? The base. I didn't show that the base is e, did I? I showed that it's logarithmic, but I didn't show that the base was e. Okay. So let's talk about that. What's the log, any base, of 1? 0. We just got that, didn't we? Plug in 1, you get 0. Right, because remember, exponentially that means b to the 0 is 1. Logarithmic expression, exponential expression, meaning the exact same thing. All right. But what's log any base of the base going to be? 1. Because this b on the bottom to the 1 is this b over here, right? So what if we set this equal to 1 and solve for x? Let's make this a variable. Whatever I got in my table here, it's log base something. Let's say I don't know. I'm telling you it's ln, but let's say I don't know. So log base I don't know what of x. If I set that equal to 1 and I solve, I should get, when this is 1, I should get the base as the argument, right? So how do you solve that equation? Okay. So the base to the 1 is x. Okay, that helped. I still don't know b. I want to get b. How do I calculate b? How do I solve for x? I know, thanks, x is b, I know that, but what number is it? Can't you solve this graphically? What if we take that function we just defined?
If b is x, then wouldn't you just be able to plug in the x's and it's itself?
It's itself, right, but that still doesn't tell me what b is. I want to know what b is. I want to know like a number,
I don't know what x
an actual number, what b is.
Yeah, it's good.
All right, now we're saying if it's ln, what's b? E, which is about 2.718 something, right? All right, so how do we get that? Well, how about we graph this. Let's graph the function that we just defined and graph y equals 1 and see where they intersect. Okay, so let's do that. So I guess I need a graph page. All right, so add a page. No? What happened there? Control, add page. Thank you. All right, let's make it a graph page. Now, can I just use the f of x from the previous page? Do I have to type that whole crazy thing out all over again? It recognizes, so I'm hoping so. All right, so enter that. Calculating. Wow, this is slow.
The what's it called? Graphing thing doesn't handle the integrals well.
Really?
Yeah, it freezes up a lot.
Wow. Wow. There it is. Does that look like a log curve to you?
Yeah.
Remember, log curves are reflections of exponential curves, right? So the inverse function of exponential should look like that. Fine. Okay, now what I want to know is where that intersects y equals 1. Now, where y equals 1, is it 2 point something? Looks like it. Let's see. All right. So how do I get another, how do I get to F2? Tab? Right, F2. I just want to put a 1 here. Okay, there you go. And I need to find the point of intersection there. That's the x value I'm solving for, right? So, how do you find that? Menu. Analyze. And intersect. Okay. And lower bound and upper bound doesn't really matter much because there's only one intersection point, but all right, how about we just can I get closer to it? No? Fine, screw you. Enter. Upper bound, can I just type it in? 3? Enter. There you go. 2.72 something. What?
Wow, this going takes forever. Mine is still,
I didn't scroll.
mine's still trying to grab.
Yeah. Well, the handheld should be easier to scroll it around. Well, this is an emulator, and it's running on an octa-core.
Mine is still grabbing.
Yeah, I just upgraded over midterm week. Sorry. So it's slow, but it's faster than it was. Okay. All right, so 2.72 something now. How do I get that number more precise? How do I get more decimals out of that? Can I?
You ask it nicely.
You ask it nicely, yeah. Can I get over there? Come on, move. Move. Why can't I move?
It's not gonna let you.
Why? All right, wait. Can I just start over again? There it is. All right, so let me get over to this thingy. Let's select it. And then what? How do you? It's so easy to do this on the handheld, right? Can you do this on the handheld?
Yeah.
It's just such a pain. See, this is just letting me move it around. I don't want to move it around. I want to like copy it to a calculator screen or something, make it bigger. All right, what about this? Menu, settings. See, float 3. Is that why I'm not getting?
Yeah, just change that.
Let's just change that, right? Okay, so how about if I make it a, what's the max I can get? Float 9 or something? 12? All right, let's make a float 12. I usually like fixed, but let's see about float. There it is. Okay, good. That's good. 2.71828182 something, right? And that's basically E. So it's a log, and its base is E, so it's log base E, and we're going to call it ln. By the way, why do they call it ln? For short. Logarithme de Napier, right? Everyone calls it, the natural log. No. Like in French, logarithme naturel. No, it's the guy who came up with this was a French guy. His name was Napier, and being French, he was vain, and he named it after himself. Logarithme de Napier, ln. Okay. All right, so let's play around with this thing.
Wait, we're not gonna do it algebraically?
Hmm?
We're not doing it algebraically?
That's it. We're done. Why? We're done. We did it. Okay, so let's use this crazy thing. What if I say y is the ln of x squared plus 3? Can you now tell me what dy dx is? I think we've done some of these before. Let's see if you remember how this works. And so we said the derivative of ln of x is 1 over x, but the derivative of ln of u is 1 over u du dx, chain rule. So 1 over u, what goes on the bottom? X squared plus 3. 1 over u times du. What's the derivative of the inside? Chain rule. So there's a 1 here times a 2x. I'm just going to put it there. Is this awful? No. Which means that you could integrate stuff like this very easily. And if you don't realize that, you can always do a u sub to figure it out. This commonly happens, yes? Things like this. 1 over u du, that fun stuff, right? Okay.
Wait, can you explain how you did that?
How did I do what? The derivative. Oh, well, we just said. The derivative of this function, ln of x, the derivative of it is 1 over x. Okay, so what's the derivative of ln of something more complicated? It's 1 over stuff times the derivative of the stuff, chain rule. You forgot the Bruno Mars song already.
Oh.
He introduced the whole thing with the ln.
You just did it all in one.
That's, yeah, sorry, do that. So isn't this a u sub? If u is x squared plus 3, du is 2x dx. We have an x dx to replace with du over 2. And so you get ln of u over 2 plus c, right? So, yeah, so now you know how to differentiate an ln of u, and you know how to anti-differentiate something involving an antiderivative of ln of u. Because you know how to do u sub, and you know this pattern now. If the top is the derivative of the bottom, you're talking about an ln. If you're integrating something where the top is the derivative of the bottom, you're thinking ln for the answer. It is. That's why it would divide it by 2. 1 over u du over 2. This is du over 2, and this is 1 over u. The integral of 1 over u is the ln, technically absolute u, and it's over 2 plus c. We'll talk about domain issues later on. But is this ever negative? So it doesn't really matter in this case. But we'll talk about domain issues later on. Alrighty. What about this one? What if y is the ln of rad cosine of x? Okay, you try that on your own. I want dy dx. So I don't ask for much. Come on. I don't know what Cheyenne. All right, so what's the derivative of that thing?
Oh, negative 10x over 2.
Negative 10 x over 2. Okay, how'd you do it? Chain rule. So what'd you do? 1 over
rad cosec
times the derivative of rad cosec. Well, that's so hard.
You gotta use the power rule for that.
Isn't the square root of anything something to the 1/2?
Yeah.
And isn't it easy to take the ln of something to the 1/2? Just bring the 1/2 out in front.
Yeah.
Okay. So it's 1/2 the derivative of ln cosine, which is 1 over the cosine times negative the sine, which is negative 10 if you like, right? And so if you're integrating tan, guess what you get?
Negative ln cosine.
It gets this crazy stuff, yes. All right, but let's just focus on the derivatives here. All right, any question how we got negative tan x over 2?
Yes, because that's not how I did it. So,
Okay, you can do it. There's more than one way to skin a cat, but you should get the same result.
but I don't know if maybe what I got is that, and I just don't know.
Yeah, you did, because cosine x to the negative 1/2 means it's in the denominator. Hang on. Cosine to the negative 1/2 means it's in the denominator, right? Then you have, that's a rad cosine on the denominator times another. The rad cosine is just cosine. So you got what I got. Sine over cosine is tan. Yep, good. All right, try that again. What if y is x squared plus 1 times rad x plus 3 divided by x minus 1? How do you get dy dx? Well, usually would say nothing really cancels. But quotient rule.
Motion rule and chain rule.
What'd you say? Calculator. Nah, you don't always have to go back to the calculator all the time. No, it's a tool, not a crutch. I didn't say crotch. I said crutch. All right, so yeah, you can do product rule, you can do quotient rule, you can do chain rule, you can do power rule, you can do all these crazy rules. But why? Differentiate that instead.
Oh, I see what you did.
Make it easy. This is called logarithmic differentiation. Makes stuff easy because products become sums, quotients become differences, and powers become products.
But there's
Oh,
no
we
L
marked that
in
as a
your
single.
original thing, so how can you?
Okay,
It's the element of everything.
just do the derivative of both sides. What's the derivative of ln of y? 1 over y dy dx. Because y is a function in x, and I'm differentiating with respect to x. So this is chain rule. If it said ln of x, and I said derivative with respect to x, you say 1 over x. But if it's 1 over y, the derivative with respect to y, with respect to x, is 1 over y dy dx. Which means I got to get this alone for the answer. How to get this alone when you're done? So you did all this craziness. How to get this alone? Multiply by the original expression. Why? Ah, okay. What's the derivative of this guy? 1 over x squared plus 1 times 2x. What's the derivative of this guy? Whoops. Well, make it easy. What did we do with the radical last time? Make it a 1/2 instead. Okay, so let's get rid of the radical and put a 1/2 in front. That's all. Make it easy. So what's the derivative of ln of x plus 3? 1 over x plus 3. And times the derivative of the inside is still 1, and there's 2 in front in the denominator. Okay. Alrighty. And what about this guy? 1 over u du, but du is, what happened to my board? Du is 1. And don't forget we're subtracting. All right, so how do you get your final answer, Regis? Multiply by y. All right, so dy dx is this whole mess. You could distribute the 2 if you want, I guess. Times y, but y was the original question, which is this. And there it is, you're done. So I didn't differentiate y, I differentiated ln of y. I made it a lot easier, believe it or not. Is that okay?
Yeah.
Should we check that with, let's check our derivatives so far with the calculator. Let's see.
The other way is a lot harder.
The other way is a lot harder, that's right, yeah. You could do it the other way, and we have done it the other way. Haven't we done product rules and quotient rules and chain rules mixed together? Yeah. All right, let's go back to the calculator, and let's get a calculator screen. Why does it always do that? Okay. And I want the derivative, the first one was ln of x squared plus 3, right? Let's check that. Right? Let's see. I'm checking this. That one. The derivative of this is this. All right, so let's check that on the calculator. So let's say menu, calculus, derivative, not at a point. And with respect to x, and it's stuck already. Aren't you good at this, stupid computer? All right, and what was it? It was ln of x squared plus 3. All right, where's ln on this beast? Second e to the right.
Second E, yeah.
All right, and then it's x squared plus 3.
No, it's plus 1.
Is it plus? No. Plus 3.
X squared plus 1 is right x.
Square plus one.
Are we looking at the wrong one?
No, you're on the first one, right?
Yeah, that's the first. That's a different problem.
Yeah, you're doing
I'm starting from here.
Oh, okay.
Yeah, I'm checking them all.
Okay.
Yeah, I'm starting from the first one we did. All right, and so what do you get? Is that what we got?
Yep.
2x over x squared plus 3. Yep, we did. Okay. All right, let's check this one. The ln of rad cosine x is negative tan x over 2. You guys ready? All righty. So ln of rad cosine x. Let's try it. So let's do the derivative. With respect to x of ln of rad cosine, right? So rad, where are you, rad? Right here. It's hard to see the blue stuff on the screen. All right, rad of cosine x. Okay, where are you, cosine?
trick cosine.
Okay, cosine x. All right, so close the cosine. No, that would be bad. Close the cosine, get out of the rad. Close the ln. Did I do that right? Well, it closed it for me? Okay, go away. And that's it, enter. Enter. Negative 10x over 2. Is that what we said?
Why does the calculator do that sometimes? That little yellow thing? I don't understand what it means. It like basically says like this could be a different answer.
Well, because there's a lot of ways of writing trig functions. So depending on how you do it or how you simplify it using trig identities, it could look different, right? But all derivatives will look the same when you graph them. If you got the same derivative a different way and it looks weird, but if you graph it, it matches, then you're okay. The problem with this gets really tricky though when you're integrating, and you get an antiderivative that doesn't look at all like anybody else's, and you graph them to compare to see if they're the same. They don't have to be the same. Antiderivatives are not unique. Why not? Because of the plus c. So it should be the same shape, same curvature, same tangent line slopes, but shifted up or down is okay. Right. So you got to check that. So I guess it's saying check. Be careful. Alrighty, and the one we just did. All right, let's try that. Now, I have a feeling it's not going to write it the way we did. Because it might, like, foil things out, combine, get common denominators and craziness. But, I don't know, let's see. All right, so let's do a derivative. And with respect to x. No, x. Of, okay, so it was this big, huge thing. How about we do a rational? All right, the numerator was x squared plus 1, quantity, x squared plus 1, times the rad of x was 3. Where's my rad? X was 3. Let's get out of the rad. Let's go to the denominator. And the denominator was just x minus 1?
Yeah.
Alrighty. And let's see what the calculator does. Oh, good luck showing that that's the same. Well, I guess we could graph them and they should look exactly the same, right? We could do that. But does that look anything like what we said?
Yeah.
I'll read.
Let's see.
Yeah.
Is this in the numerator anywhere? Is it?
Yeah.
Are you combining? Ugh.
You see the rad x plus 3 all over the place.
Yeah. Yeah. We could combine, get it common denominators and multiply this out and show it algebraically. It's probably the same thing. But let's see. You got 2x rad x was 3 over x minus 1. Okay. And then you got minus x cubed over that stuff. That's just the common denominator. That's all that is. Minus 7. Wow. Where does 7 come from? Well, we could graph it, I guess.
The 6 and the 1's from the main 7.
How do you unfreeze a
Yeah, it
calculator?
won't even let me shut it off.
Take it
Step
out.
on it.
Please,
Really
Like when
hard.
we were trying to graph that thing before, it's still loading.
It's still graphing that thing?
No, no.
Well, okay.
Press the restart.
reset.
Yeah, what's the reset? What are you telling?
And then it stops whatever function.
Oh, the one on the back. Yeah, how do you do that? I haven't had to do that.
Just
Oh,
go
the
to
pin
back.
thing? Okay. Alrighty. How about this one? Alright, let's see you do it. Let's integrate. We talked about one similar to this. You really have to do the pin thing, Jorge? There's no other like reset key? What did you do?
Too small to go.
What?
Either hold escape and on or control on.
And eventually just reset?
Escape
on, control on.
It just stops whatever process you're
Huh?
running.
Well, that's just using it enough and it went to sleep. It was bored. All right, so how do you do this? Any ideas?
Yeah.
Yusuf, you is? Oh, who's in AP English? You is? U is x squared plus 3, so du is 2x dx. So what are you replacing? You tell me. I don't know nothing.
1/2.
Yeah, you're going to replace the x dx with, what is it? D over 2. So I'm going to say it's du over 2 and over u. So now it's easy. 1 over u du integrates as ln. So equals the 1/2 the ln of absolute u plus c. The absolute value is a problem because, remember when we graphed it? Did you see the graph? Did it ever cross the y-axis? So can you do ln of 0? Can you do ln of negatives? Right? So make sure you're only plugging in non-negatives. Yeah, the 0 is not allowed either. All right, and you're not done because, can we rewrite this in terms of x if you want? So what is it? 1/2 the ln of x squared plus 3, right? Okay. Plus c. What if you had, I don't know, limits of integration? Like, what would be good? I don't know, just make up something. 1 to 2. Do you have to do the plus c? No. Do you have to go back to x's? No. You can change the limits of integration to what? 4 to 7. Okay. So then, you don't have to do this. You don't have to do this. Well, because if x is 1, plug it in, u is 4. And if x is 2, plug it in, u is 7, right? And so, we're going to do this. And you get 1/2 the ln of 7 minus the ln of 4, quantity 1/2. How about that? All right, do you want to check that? Let's check that. You ready? Everyone got that?
Yep.
Which might simplify, but it's nothing special here. 2 of ln 2. Yeah, it's not much you can do here. 7's already primed. All right, I picked unwisely. All right, but let's see. So we're integrating. Okay. All right, so what are we integrating? We're doing menu, calculus, integral
Yes, sir.
of. Well, let's do the antiderivative first.
I haven't seen it. Come for that 80 though.
Why is it stuck? Oh. All right, so let's do the antiderivative alone. X over x squared plus 3.
I've had Dennis on my team before. Yeah, that works out pretty good.
With respect to x. All right, is that what we said? 1/2 ln of u. Right, we did. Okay. Now let's do it. Can we just copy this and add limits of integration?
Oh, that was the easiest project I ever did. You could really want 30 minutes of
No, we can't. Okay, forget forget that. All right, so let's do menu, calculus, integral, and we're going from 1 to 2 of x, let's see, rational, x over
Air resistance.
x squared plus 3
Terminal velocity.
with respect to x. And is that the same thing as that?
Yeah.
The ln of 7/4 is the ln of 7 minus the ln of 4, and it's being divided by 2. And if you want a decimal, there it is, 0.279 something, or 280. 280, 3 places, okay? Any questions on ln? No. Derivative of ln or antiderivatives involving ln? Okay, we're good. So, that was fun, YouTube. Have a nice day.